Welcome to Mydreamsacademy.
Welcome to Mydreamsacademy online tutorial. My name is Benjamin Sunday, just like you know me by name Masakka. Our topic today is bonding in chemistry. Alright, our topic today, just like I've told you, is bonding. Basically, we have two types of bonding: chemical bonding and secondary bonding. You may call chemical bonding interatomic bonding because it will exist between two atoms during chemical reaction. Then you also call it primary bonding because that is the first type of bond that will exist before bond between molecules. Of course, you know molecules are formed by interaction between atoms. One, two or more atoms, when they interact, they can give you a molecule. So before a molecule can form, atoms must unite together to form molecules. And then bond existing between atoms are now primary bonding, because that's the first type of bond that will exist. Then the one that will not exist between the molecules formed now, you now call it secondary bonding or intermolecular bonding, meaning that it will exist between molecules. That's why you call it intermolecular. Then you call this one interatomic because it will exist between atoms. Now, we now want to take on chemical bonding. What is chemical bonding? Chemical bonding involves covalency and electrovalency. Covalency and electrovalency. The question now is, what is covalency? Covalency is the process of sharing two electrons between two atoms, while electrovalency is the process of electron transfer from one atom to another. So these two processes, covalency and electrovalency, give rise to chemical bonding. Now let's go into electrovalency as the basis of chemical bonding, and that will now lead us to the fact that you have three main types of chemical bonding. Three main types. There are three main types of chemical bonding. What are the three main types of chemical bonding? One is ionic bonding, or you call it electrovalent bonding. Then two is covalent bonding. Then three is metallic bonding. These are the three main types of chemical bonding: ionic bonding or electrovalent bonding, covalent bonding, and then metallic bonding. Now let's look at ionic bonding, and then before that after which we're now going to covalent and metallic. Let's now go into ionic bonding. Remember that bonding is simply process of forming bond. Now, what is ionic bond? An ionic bond is an electrostatic attraction between a metal ion and an anion formed by electron transfer. So by this, we mean that, of course, you know that a metal normally ionized by losing an electron. Then non-metal ionized by gaining an electron. For example, sodium, you know, has 11 electrons, 1 on the valence shell. It can lose 1 electron and form sodium ion, which is a cation. And now, how will it lose it? Remember that no element can start reacting unless there is something. That's why we have the word chemical reaction. Before you have reaction, there must be action. So the non-metal will bring an action by coming closer to a metal so that it will be ready to accept electron from a metal. So for example, now sodium can lose 1 electron. If sodium should come closer to chlorine, for example, sodium can lose the electron. And when it loses electron, it forms this. Then this one can gain that 1 electron and form this. You now see that they can now, you will now have a metal ion and non-metal ion. So there is now an attraction. Why we call it electrostatic, in the sense that two of them are not moving, they are one place. That is why you have static. Electro is telling you that the two forces, the force is there, or the very force is as a result of attraction between positive electrical charge and negative electrical charge. That is what ionic bond is all about. Now, as you have seen, ionic bond is not all about knowing just ionic bond. We must know condition, because it is easy saying that sodium can transfer electron, chlorine will gain it. How do we know the possibility of a metal transferring an electron and the possibility of another one gaining it? So we now have 3 favorable conditions. 3 favorable conditions for ionic bond formation. One is number of valence electron. One is that the metal, ionic bond formation between a metal and a non-metal. Let's just be specific. One is that the metal should have 1 or 2 or 3 valence electrons. While the non-metal should have 5 or 6 or 7 valence electrons. Now class, we say that one condition for ionic bond to form between a metal and non-metal is that the metal should have 1 or 2 or 3 valence electrons. Remember that valence electrons are the electrons that occupy the atomos shell, the most atomos shell of an element or an atom. The metal should have 1 or 2 or 3 valence electrons, while the non-metal should have 5 or 6, 7 or 7 valence electrons. Now, let me ask you a question. Look at sodium, for example. You know the electron structure of sodium, it can be represented this way. The innermost shell has 2 electrons, then the outer one here has 8, then the outermost, which is the valence shell, now has 1. Then if I talk about chlorine, for example, you know the atomic number of chlorine is 17. Chlorine is 17, which means you can represent the electronic configuration of chlorine to be 2, 8, and 7, meaning that the inner shell can have 2 electrons. The second shell, you have 8. The outermost one is 7. So you can now see that based on this condition 1 now, that the metal should have 1 or 2 or 3 valence electrons, while the non-metal should have 5 or 6 or 7 valence electrons. It means that sodium, which has 1 valence electron, and chlorine, which has 7 valence electrons, can now interact to form an ionic bond. They can, because this condition now is satisfied. But let me also tell you this, that remember that an element that has, or a metal that has 1 valence electron, it will be faster for it to lose it than a metal that has 2 valence electrons. Of course, you know that metals normally do repair themselves. Okay, sorry, electrons do repair themselves in the atom. So electrons that are 2 will be difficult to be lost than electron that is just singly present in the valence shell. So therefore, please pardon me, therefore a metal that has 1 valence electron will lose it faster than a metal that has 2 valence electrons. And then non-metal that has 7 valence electrons will easily accept that very one to attain octet state, which is electron octet. What I mean by electron octet is that one electron once one electron is transferred here now, it becomes 8. Okay, so that is when you now have something like this. Assuming that chlorine should gain 1 electron, now you can now have something like this, which means that this thing has attained an electron octet, which is 8 electron, 2, 8, 8 electron octet. Okay, so that is it, please. Now also, it will be faster for a metal that has 2 valence electron and non-metal that has 6 valence electron to form an ionic bond than a metal that has 3 valence electron and a non-metal that has 5 valence electron. As you can see, 1 plus 7 is 8, and 2 plus 6 is also 8, and 3 plus 5 is also 8. So this 1 and 7 combination will give you octets, and 2 and 5 combination will give you octet as well. 3 and 5 combination will still give you octet. So which means that metal that has 1 valence electron will form a ionic bond faster with non-metal that has 7 valence electron, and a metal that has 2 valence electron will also form a ionic bond faster with a non-metal that has a 6 valence electron than it will form with non-metal that has 5 valence electron. Now the second condition is high electronegativity difference. High electronegativity difference, that is second condition. For ionic bond to exist between a metal and a non-metal, the electronegativity difference between them should be greater than 1.6. Should be greater than 1.6. We have said that high electronegativity difference will favor ionic bond formation. And I will give you a kind of rule that for ionic bond to exist between a metal and a non-metal, the electronegativity difference between them should be greater than 1.6. Should be greater than 1.6. Now let me show you this. Look at sodium chloride. Let us see the possibility of sodium and chlorine forming an ionic bond. Electronegativity of sodium is 0.9, in line with Pauling. That's why using Linus-Pauling scale. Linus-Pauling electronegativity scale. So from Linus-Pauling electronegativity scale, the electronegativity of sodium is 0.9, chlorine is 3.0. Now what's the difference now? 3 minus 0.9. 3 minus 0.9 will give you what, class? What? It will give you 2.1. Thank you. Now that 2.1, as you can see, we said that the difference should be greater than 1.6. The difference should be greater than 1.6. But now the difference is 2.1. So can ionic bond form between sodium and chlorine? Yes. Yes. The answer is yes. Because the 2.1 is greater than 1.6. Watch again. Something like aluminum and oxygen, can they form ionic bond? Let us see. The electronegativity of aluminum is 1.5, oxygen is 3.5. Now class, what is the difference? Difference is 3.5 minus 1.5, which will give you what? 2.0. So as you can see, 2.0 is still greater than 1.6. So which means aluminum and oxygen will form an ionic bond. Just like we've said before, that of course you know aluminum has 3 valence electrons, and then oxygen has 6 valence electrons. 6 valence, then aluminum has 3. So there is a combination between this and this now. Although we are coming to see how stagically how the bond is actually formed between aluminum and the oxygen. Okay. Now maybe that will be in our next edition. Now aluminum. Let's also talk about. Let's talk about something like magnesium and oxygen, whether they will form ionic bond or not. Oxygen is still 3.5. Magnesium is still 1.2, as different as you saw the electronegativity value. So what is the difference now? Difference is 3.5 minus 1.2, which will give you what? It will give you 2.3. Now as you can see, 2.3 is far greater than 1.6. So magnesium and oxygen will form ionic bond. So class, this is how you can use this rule to know when you have ionic bond formed between 2 atoms, please. Now the third condition now is net lowering of energy. Net lowering of energy, or okay, let's just, what does this mean? There should be net lowering of energy. What this means that there should be release of energy. There should be release of energy. Now, what does this mean? Let me take it back small. If we look at how sodium chloride is formed, let's look at how sodium chloride is formed. So let me, to illustrate what I mean by net lowering of energy, or by saying that there should be release of energy, let us consider how sodium chloride is formed. Formation of sodium chloride. Formation of sodium chloride. Now, you know that sodium is a metal, and being a metal is also a solid. So first of all, and you know, metals exist in crystalline form, in the sense that the atoms are locked up in a particular, arrangement known as crystal lattice. So the sodium crystal cannot just react like that. An atom is supposed to be isolated, and now to do that we require some amount of energy, okay, to be able to convert, to isolate an atom, to extract a sodium atom from that crystal, or that bulk of sodium atoms. Now we need a certain amount of energy to be able to do that, because for you to have isolated a sodium atom from a crystal of sodium, you have converted that very atom to gaseous state. So this process is called sublimation, because a solid atom has been converted to a gaseous atom. So the energy required here, the enthalpy change for this process is called enthalpy of sublimation enthalpy, which is positive. Now, this state now, sodium is now in excited state, so it cannot lose electron. It cannot lose electron in this state. It cannot lose electron to form a sodium ion. So actually the standard enthalpy for this process is called enthalpy of ionization energy. This is ionization energy. So you see, sodium ion has formed by losing an electron. It has actually lost one electron. So now let us now see that of chlorine. Of course, you know that chlorine exists in molecular form. It says that two atoms are held by covalent bond. So first of all, the bond needs to be broken so that you can convert very chlorine molecule to atom. Okay, in gaseous state as well. So this process requires a certain amount of energy we call atomization energy or bond dissociation energy, which is also positive. Enthalpy here is also positive. This is bond dissociation energy. Now we have converted molecule to atom. Chlorine atom rather, can now gain that very electron that sodium transferred. And you now have chloride ion. So certain amount of energy is given out here. That energy given out there is called electron affinity. Electron affinity is negative. The minus sign here indicates that the energy is being given out. Okay, because what that means, of course, you know, energy was required here for sodium to lose the electron. So chlorine should also accept, in trying to accept that electron, it should release maybe energy equivalent to such amount of energy. So now that the chloride ion has formed, sodium ion has formed, sodium ion formed by this one releasing an electron, and chlorine will now gain that very electron, chlorine atom rather, to give you chloride ion. So the next stage now is the interaction, the attraction between this sodium ion and chloride ion, which will now give us this sodium chloride molecule. Then energy is also given out here. The energy given out here is called lattice energy. So that is the enthalpy of this process. Lattice energy, which is negative, because the energy is given out. Lattice energy, LE. So now watch. What do we mean by net lowering of energy is that the amount of energy required here, if I sum up this energy plus this very one, all this amount of energy that we absorb together, and those that were given out, if I add this and I add this, there should be, the total amount of energy here and here, if add up this and this, should be greater than what we get when we have added up this. So that will now make it possible for energy to be lost. Of course, this very lattice energy is telling you, the magnitude of the lattice energy is telling you the amount of force, the magnitude of the ionic force or the bond between the very two ions in the compound, in ionic compound. So that is why we say that there should be net lowering of energy, meaning that, of course, the lattice energy should be high enough, because that's actually the controlling factor. It should be high enough. Having considered factors favoring formation of ionic bond is also important that we consider factors governing ionic bonding. One is high electron affinity. High electron affinity of the non-metal. 2 is high lattice energy. High lattice energy of the ionic compound. Three is high electronegativity difference. Alright, of course we have talked about this before. We've also talked about electron affinity. Of course, let me just tell you what electron affinity. Electron affinity has to do with the amount of energy absorbed or released when an electron is added into the valence shell of a gaseous atom. Please take note of this. It could be energy released, it could be released, it could be absorbed, which means the process can be endothermic or exothermic. There are some atoms that release energy. There are some atoms that release energy when they gain electron. There are some also that will absorb energy when they gain electron. So please take note of it. It could be energy absorbed, it could be absorbed, it could be released. There are just something like chlorine. Chlorine, on gaining electron, will lose energy. It will release energy to the environment. So because it will release energy to the environment, enthalpy is negative. But something like oxygen, actually, when oxygen atom gain the first electron, you have something like this. And then the process here is still negative. The energy is negative. This is electron affinity, please. But for the electron to go into another electron, for this very, of course, you know that this thing is not, oxygen does not exist this way. Oxide ion does not exist this way. So this will further accept the electron again. By accepting another electron, energy is absorbed. So since energy is absorbed, the enthalpy change is now positive. So that's why we say that energy could be absorbed, it could be released. In this one, in this stage, in the first electron affinity, it was released. In the second one, let's now look at covalent bonding. What is a covalent bond? A covalent bond is a pair of electrons shared between two atoms. Please. Pair of those two electrons shared between two atoms. That is what is covalent bonding. Now, having discussed or defined what covalent bonding is, there are many types of covalent bond, but we have to be very careful here. Now we're talking about sharing of two electrons being shared by two atoms. Now there are ways that sharing can happen. The two atoms that will share the electron may contribute each of the two electrons. Then one will also decide to contribute the two electrons, the entire electrons. That will now lead us into having two major types of covalent bonding, two major types, which we may call normal covalent bonding. There are many criteria anyway. Normal covalent bonding, or you may call it normal covalent ordinary covalent bond. Ordinary covalent bond. What is normal? Of course, the normal is telling you that each of the two atoms contribute one electron. That is why you have normal ordinary. So of course, when each of the two electrons shared was contributed by each atom. So when each of the two atoms reacting contribute one electron, the bond that has formed is normal covalent bond. So that is the first type. Then the second one now is coordinate or dative covalent bond. When does this one occur? This one occurs when the two electrons shared were contributed by only one atom, only one of the two bonding atoms. So in normal covalent bond, only each of the two atoms contribute one electron, but in coordinates, only one will contribute the two electrons. That's why you have the word coordinate. It's a special type of covalent bond. But mind you that all covalent bond involve sharing of two electrons, whether normal or coordinates. Okay? So now, that is on that. We'll now go into all this covalent bond here, whether normal or coordinates, can be polar or non-polar. Because we're now going to talk about polar bonds now. Polar bonds. What is a polar bond? A polar bond is a bond that has both covalent character and ionic character. That is a polar bond. So it is possible for a bond between two atoms to have both ionic character and covalent character. So whether a bond is normal, whether a covalent bond is normal or coordinate, it may be polar. Okay? So now, when do you know that a bond is, what criteria will help us to know that a bond will be polar? That is now a question. Look at it. For a bond between two atoms to be polar, the electronegativity difference should be greater than 0.5. So if the electronegativity difference between two atoms is greater than 0.5, then expect polar covalent nature. So the polar bond, meaning that that bond will now have some ionic character and some covalent character. Let me give for example something like a bond between carbon and hydrogen. Let's see whether it will be polar or not polar. Electronegativity of carbon according to Linus Pauling scale is carbon is 2.5 and hydrogen is 2.1. What is the difference now? The difference in electronegativity is 2.5 minus 2.1, which is 0.4. You see, the electronegativity difference is 0.4 and is less than 0.5. which means that the bond, covalent bond, the bond here between carbon and hydrogen is not polar, is non-polar. Okay, and of course I'm going to tell you what I mean by that polarity or non-polarity, because that polarity is telling you that these electrons here were not equally shared. They were not equally distributed. That one element is pulling more electron closer to itself than the other one is pulling. Okay.
Welcome to Mydreams Academy.